Welcome to Mech Cosmos. Imagine you are sitting on a plane somewhere over the Atlantic Ocean. It is the middle of the night. Everyone around you is asleep. And you are staring out the window into complete darkness. And then it hits you. You are sitting in a metal tube, 35,000 feet above the ground. That is almost 11 kilometers up. The temperature outside is minus 60 degrees Celsius. And you are moving at 9-10 kilometers per hour. That is faster than most military jets from World War II. And you start thinking, what is actually keeping this thing up there? Because here is what most people do not realize. A Boeing 747, the classic jumbo jet, weighs 315,000 kilograms during a typical flight. That is not the maximum takeoff weight. That is the mid-flight weight, after burning thousands of liters of fuel. 315,000 kilograms. That is the same as 50 fully grown African elephants, or 3,000 average-sized cars, all flying through the air at once. Most people, when you ask them, say, well, the engines push it forward, right? And yes, that is true. But that does not explain why it stays up. If you throw a rock forward really fast, it still falls to the ground. Speed alone does not create lift. The real answer, the actual physics of why a plane stays in the air, is happening somewhere most passengers never look. Out there on that wing. That weird, curved, oddly shaped wing hanging outside your window. Today we are going to take that wing completely apart. We are going to look at the real numbers, the actual physics, the history. And I am going to show you something that even surprises most engineers. That scientists have been arguing about the exact explanation for over 120 years. Let us get into it. Before we can talk about wings and lift and pressure, you need to understand one fundamental concept. Because without this, nothing else makes sense. Every single aircraft that has ever flown, from the Wright brothers' first fragile wooden biplane in 1903 to the Airbus A380 carrying 850 passengers today, every single one of them is constantly fighting four forces at the same time. These four forces are lift, gravity, thrust, and drag. Four arrows, each one pointing in a different direction. And the entire science of flight is basically about managing the relationship between these four things. Let us go through each one. Force number one is gravity. Gravity pulls everything down, always, without exception. It does not matter how fast you are going, how high you are, how powerful your engines are. Gravity never stops pulling. For our 747 at 315,000 kilograms, gravity is pulling it downward with a force of over 3 million newtons, every single second of the flight. That is an enormous force that the airplane has to constantly fight against. Here is something interesting. The weight of the plane actually changes constantly during the flight. Why? Because fuel is heavy. A Boeing 747 burns roughly 11 liters of jet fuel every single kilometer it flies. On a long transatlantic flight, it burns over 100,000 liters of fuel. So the plane that takes off weighs significantly more than the plane that lands. This means the pilots and the aircraft systems are constantly adapting to a changing weight. Force number two is thrust. Thrust is the force that pushes the airplane forward. It comes from the engines. Without thrust, there is no speed. Without speed, there is no flight. We will talk about exactly how jet engines create thrust later in this video. And trust me, it is fascinating. But here is something important to understand right now. Thrust does not lift the plane. Thrust pushes the plane forward. Lift, which we will get to, is what pushes the plane upward. They are two completely separate forces, doing two completely separate jobs. Force number three is drag. Drag is air resistance. When you move through air, the air pushes back against you. Every surface of the airplane, the fuselage, the wings, the landing gear, even the antennas, creates drag. The faster you go, the more drag you experience. This is why airplanes are so carefully shaped. Every curve, every angle, every rivet on the surface of a modern aircraft has been engineered to reduce drag as much as possible. Here is a number that puts drag into perspective. At cruising speed, the engines of a 747 produce around 280,000 newtons of thrust just to maintain constant speed against drag. If the engine stopped, the plane would gradually slow down and descend. not fall out of the sky instantly, which is a common misconception. Force number 4 is lift. And here we are, the star of the show. Lift is the upward force that keeps the plane in the air. It counteracts gravity. In level flight, lift equals weight exactly. If lift is greater than weight, the plane climbs. If weight is greater than lift, the plane descends. The big question, the question that took humanity thousands of years to answer, is where does lift come from? How do you generate an upward force from something as invisible and seemingly insubstantial as air? To answer that, we need to travel back to 1738 and meet a Swiss mathematician who changed everything, Daniel Bernoulli. Born in 1700 in the Netherlands, raised in Switzerland. A mathematician and physicist from one of the most remarkable scientific families in history. His father Johann and his uncle Jakob were both famous mathematicians. Family dinners must have been interesting. In 1738, 165 years before the Wright brothers flew, Bernoulli published a book called Hydrodynamica. In it, he described a principle that at first glance seems completely backwards. Fast-moving air has lower pressure than slow-moving air. Read that again. Faster air means lower pressure. Slower air means higher pressure. This feels wrong. If someone blows air at you really hard, you feel pushed. But that is the force of the moving air hitting you. That is not the same as the pressure within the airflow itself. Bernoulli spoke about the static pressure within a flowing stream of air. And here is the best analogy I know for this. Think about a river. A wide, slow river is flowing along peacefully. Then suddenly, the riverbanks narrow. The same amount of water has to pass through a smaller space in the same amount of time. So what happens? The water speeds up. Now, and here's the key insight, the water that is moving fast through the narrow section is actually at lower pressure than the slow water in the wide section. This is why, if you put a ball in a fast-flowing stream, it gets pushed toward the center of the stream, not away from it. The fast-moving water in the center has lower pressure, and the slower water at the edges pushes the ball inward. Bernoulli discovered this principle for fluids, and air is a fluid. It behaves by the same rules. Now look at a wing cross-section. See the shape? The top surface is curved. It bulges upward. The bottom surface is much flatter. This shape is called an airfoil, and it is one of the most important shapes in human history. When the plane moves forward, air hits the front edge of the wing and splits in two. Some air goes over the top. Some air goes under the bottom. The air going over the curved top has a longer path to travel. To keep up with the air going under the flat bottom, to meet at the trailing edge of the wing at the same time, it has to move faster. Faster air over the top means lower pressure over the top. Slower air under the bottom means higher pressure under the bottom. Higher pressure underneath pushing up, lower pressure above pulling up. The result, the wing gets pushed and pulled upward. That is lift. Now let us talk real numbers, because this is where it gets genuinely mind-blowing. At cruising altitude, the atmospheric pressure around the aircraft is about 23,800 pascals. On top of the wing, the pressure drops to roughly 23,400 pascals. Under the wing, it is about 24,000 pascals. The difference between the top and the bottom? Only about 600 pascals. That is less than 2% of the surrounding air pressure. Tiny. Barely anything. But here is what makes it powerful. Pressure is force per area, and the wings of a Boeing 747 have a total area of 525 square meters. That is bigger than a basketball court. When you apply even a tiny pressure difference across 525 square meters, you get an enormous force. Let us do the math together. To keep our 747 in the air, every single square meter of wing needs to generate approximately 600 kilograms of lift. 600 kilograms per square meter, every second. The entire time the plane is flying. That is the Bernoulli principle at work. An invisible pressure difference, spread across an enormous surface, generating hundreds of tons of upward force from nothing but air. But, and I need to be honest with you here, Bernoulli alone does not tell the whole story. And this is where it gets controversial. There is a common explanation you have probably heard. It goes like this. The air going over the top has a longer path, so it has to move faster to meet the air from the bottom at the trailing edge at the same time. This is called the equal transit time theory. Here is the problem. It is not entirely accurate. In reality, the air over the top does not need to meet the air from the bottom at the same time. Experiments with smoke tracers in wind tunnels have shown that the air over the top actually arrives at the trailing edge significantly before the air coming under the bottom. The equal transit time idea is a simplification that has been repeated in textbooks for decades, but it is not the real reason the air speeds up. The air speeds up over the top because of the shape of the wing. The curve forces the airflow to accelerate, regardless of what the air underneath is doing. The pressure difference is real. The lift is real. The exact mechanism is just slightly more complicated than the simple explanation suggests. This is one of the things I love about physics. Even something as everyday as an airplane wing still has scientists debating the fine details. But Bernoulli is only half the story. There is a second force at work, and for this one we need Isaac Newton. Isaac Newton, 1687. Third law of motion. For every action, there is an equal and opposite reaction. You already know this law intuitively. When you fire a gun, the bullet goes forward and the gun kicks backward. When a rocket burns fuel downward, it goes upward. Action and reaction. Now look at that wing again. Notice something. The wing is not perfectly horizontal. It is tilted slightly upward at the front. This tilt angle is called the angle of attack. It is the angle between the wing and the oncoming air. Here is what this angle does. Because the wing is tilted, the oncoming air does not just flow over and under it smoothly. The bottom of the wing catches the air and deflects it, pushes it downward. Massive amounts of air are being pushed downward by the wing every second. Thousands of kilograms of air being deflected toward the ground. Newton's third law. If the wing pushes air down, the air pushes the wing up. Equal and opposite reaction. This is the second source of lift, and this one is actually easier to feel intuitively. You have experienced it yourself. Next time you are in a car on the highway, stick your hand out the window. Carefully, please. Hold it flat and level. You feel drag. The wind pushing your hand straight back. Now tilt your hand so your fingers point upward at an angle. Suddenly your hand gets pushed upward. You are deflecting the air downward with your hand, and the air is pushing your hand upward in reaction. Your hand is acting exactly like a wing. A very small, not very aerodynamic wing, but the same principle. A wing is just a highly engineered, enormously efficient version of your tilted hand. So we now have two sources of lift working together. Bernoulli's pressure difference from the wing shape, and Newton's deflection force from the angle of attack. In reality, you cannot separate them. They happen simultaneously. Modern aerodynamics understands lift as a combination of both effects. But this angle of attack, this tilt, has a critical limit. And exceeding that limit is one of the most dangerous things that can happen to an aircraft. The stall. Two words that make every pilot's heart rate go up. Here is what happens. As you increase the angle of attack, tilt the wing more and more steeply into the oncoming air, lift increases. More deflection, more pressure difference, more lift. This works beautifully up to a point. On a typical commercial airliner, that point is around 15 to 18 degrees. Beyond that angle, something catastrophic happens to the airflow. The air rushing over the top of the wing can no longer follow the surface. The curve is too steep, the angle too extreme. The smooth, organized airflow, what engineers call laminar flow, breaks apart. It separates from the wing surface and becomes chaotic, turbulent, completely disorganized. The pressure difference that generates lift collapses. Lift drops suddenly and dramatically. The plane falls. Now before you panic on your next flight, understand this. Stalls do not happen by accident in normal commercial aviation. The aircraft computers, the autopilot systems, the flight envelope protections, they all prevent the angle of attack from getting anywhere near the stall point during normal operations. But there is something critically important that you must understand about stalls. And this is where many people, including some pilots, have a dangerous misconception. A stall has nothing to do with engine failure, nothing to do with speed directly. A stall is purely about the angle of attack exceeding that critical 15 to 18 degree limit. This means a plane can stall at any speed, even at high speed. If a pilot pulls back too aggressively on the controls, yanks the nose up hard, the wing can exceed its critical angle of attack even while moving fast. This is called a dynamic stall or accelerated stall, and it is just as dangerous as a low-speed stall. This brings us to one of the most tragic aviation disasters in modern history. Air France Flight 447, June 2009. A flight from Rio de Janeiro to Paris. An Airbus A330 carrying 228 people. In the middle of the night, over the Atlantic Ocean, the aircraft encountered a weather system. Ice crystals blocked the external airspeed sensors, called pitot tubes. The autopilot disconnected because it could not trust the speed readings. The co-pilot, in a moment of confusion and panic, pulled back on the side stick. He raised the nose of the aircraft. Way too much. The angle of attack shot past the stall limit. The aircraft stalled at 38,000 feet. For 4 minutes and 23 seconds, the aircraft fell. The crew received continuous stall warnings, a recorded voice repeating stall, stall, stall. But the co-pilot kept pulling back on the controls, which was exactly the wrong thing to do. To recover from a stall, you must push the nose down to reduce the angle of attack and let the wings start flying again. But he kept pulling. All 228 people on board died. The accident fundamentally changed how pilots worldwide are trained to respond to stalls. It remains one of the most studied, most analyzed accidents in aviation history. And at its core, it was a story about angle of attack and a wing that stopped flying. Modern aircraft have multiple stall warning systems. There is the stick shaker, a mechanical device that physically vibrates the control column violently to wake the pilot up. There are angle of attack indicators. There are automated voice warnings. And in the most modern aircraft like the Boeing 787 and Airbus A350, the flight computers will actually prevent the pilots from exceeding the stall angle no matter how hard they pull. The computer overrides the pilot's input to protect the aircraft. The stall is the fundamental limit of every wing ever built. Understanding it is understanding the most important boundary in all of aviation. Now let us talk about what gets the wing moving fast enough to generate lift in the first place. The jet engine. What you are looking at when you see a jet engine cutaway is one of the most complex, most precisely engineered machines ever created by human beings. A modern turbofan jet engine, like the ones on a 747, operates at temperatures hotter than the surface of the sun inside the combustion chamber. It spins at over 10,000 revolutions per minute. It is made of thousands of individually precision-machined parts, and it has to do this continuously, reliably, for tens of thousands of flight hours without failing. Let us walk through exactly what happens inside. Step 1 is air intake. The front of the engine is essentially a giant mouth. At cruising speed, a large turbofan engine swallows approximately 1.2 tons of air every single second. Think about that. 200 kilograms of air entering the engine every second. The large front fan you can see when you walk past a plane at the airport, that fan is pulling in massive amounts of air and directing it into the engine. Step 2 is compression. After the fan, the air enters the compressor. The compressor is a series of spinning blades that squeeze the air, compress it, into a much smaller space. This is critical. By the time the air reaches the combustion chamber, it has been compressed to about 40 times its original pressure. 40 times. The air that entered at normal atmospheric pressure is now squeezed into a tiny fraction of its original volume, which makes it incredibly hot and dense. Why compress it? Because compressed air burns much more efficiently. More energy is released from the fuel when the air is dense and hot. Step 3 is combustion. The compressed air enters the combustion chamber, where jet fuel is injected and ignited. This is where the temperatures exceed 1,500 degrees Celsius. hotter than the melting point of the metal the engine is made from. The only reason the engine does not melt is because of incredibly sophisticated cooling systems. Tiny holes in the turbine blades that pump cool air through the metal to keep it below its melting point. An engineering solution so clever, it deserves its own video. The burning fuel-air mixture expands explosively. Hot, high-pressure gases rush toward the back of the engine at enormous velocity. Step 4 is the turbine. Before those hot gases escape, they pass through the turbine. The turbine is a set of blades that the hot gases spin as they rush past. This spinning turbine is connected by a shaft to the compressor at the front of the engine. So the exhaust gases are powering the compressor that is compressing the incoming air. The engine is partially self-sustaining. The energy from combustion drives the compression of the next cycle's air. Step 5 is exhaust and thrust. The remaining hot gases shoot out the back of the engine at high velocity. This is where Newton's third law appears again. Hot gases going backward at high speed, aircraft going forward at high speed, action and reaction, thrust. Now here is something interesting. On a modern turbofan engine, the type used on almost all commercial aircraft, the majority of the thrust actually does not come from the hot exhaust gases. It comes from the large fan at the front. That big fan bypasses most of the air around the engine core entirely. It pushes a massive volume of cold air backward without burning it. This bypass air provides more thrust and is far more fuel efficient than burning more fuel. On a modern high bypass turbofan, roughly 80% of the thrust comes from the fan, and only 20% from the hot exhaust. This is why modern jet engines are so much quieter and more fuel efficient than the early jet engines of the 1950s and 1960s. The thrust numbers are staggering. Each engine on a Boeing 777 produces about 513,000 newtons of thrust. That is the equivalent of lifting approximately 52,000 kilograms, 52 metric tons, straight up. And a 777 has two of them. Now here is something that puzzles a lot of people. A commercial airliner cruises at around 900 kilometers per hour, but it lands at around 270 kilometers per hour. That is less than a third of its cruising speed. The problem is this. At 270 kilometers per hour, the wing does not generate nearly enough lift to support the weight of the aircraft. At that speed, with the normal cruise wing shape, the plane would simply fall out of the sky. So how does it land? The answer is that the wing literally changes its shape during landing. And this is something you can watch happen if you sit over the wing on your next flight. Watch the trailing edge, the back edge, of the wing as the plane begins its descent. You will see large panels extend and drop downward. These are the flaps. Flaps do two things simultaneously. They increase the surface area of the wing, making it physically bigger, and they change the camber of the wing, the curvature, making it more curved, which generates more lift at lower speeds. The result is that the same wing that cruises efficiently at 900 kilometers per hour can also generate enough lift to fly safely at 270 kilometers per hour with the flaps fully extended. But flaps create a trade-off. Yes, they generate more lift, but they also create dramatically more drag. At cruise speed, all that extra drag would require enormous amounts of extra thrust, burning massive amounts of extra fuel. So flaps are retracted completely during cruise, and only extended for takeoff and landing when you need extra lift at low speeds and you do not mind the extra drag. There is also another device called slats, leading edge devices that extend from the front edge of the wing. They work similarly to flaps, further increasing the wing's ability to generate lift at low speeds. Together, flaps and slats can increase the maximum lift of a wing by 70 to 80% compared to the clean cruise configuration. Next time you are on a plane, watch the wing during takeoff and landing. You will see the whole trailing edge transform. It is one of the most elegant pieces of mechanical engineering you will ever witness from a passenger seat. Before we wrap up, let me hit you with some genuinely mind-blowing facts about flight that most people, including most frequent flyers, do not know. Fact number 1, wings flex. A lot. The wings of a Boeing 787 Dreamliner can flex upward by up to 7.6 meters at the tips during flight. 7.5 meters. The wings are not rigid, they are designed to bend. This flexibility actually makes the wings stronger and more efficient, like how a fishing rod bends without breaking. If the wings were completely rigid, the stresses from turbulence and maneuvers would eventually crack the metal. Fact number 2. Turbulence cannot bring down a modern airliner. I know turbulence feels terrifying, but the aircraft you are sitting in has been tested to withstand forces far beyond anything it will ever encounter in normal flight. Modern commercial aircraft are certified to handle loads of 2.5 times the maximum expected stress, and they are tested to 1.5 times even that before certification. No commercial airliner has ever been brought down by turbulence alone. Fact number 3. If both engines fail, the plane glides. A commercial airliner without any engine power has a glide ratio of roughly 15 to 1. For every 1 kilometer it descends, it travels 15 kilometers forward. At cruising altitude of 10,600 meters, a powerless 747 could glide approximately 150 kilometers before reaching the ground. This is actually what happened with Air Canada Flight 143 in 1983. Both engines failed due to a fuel miscalculation, and the crew successfully glided the aircraft to an emergency landing on a disused airstrip. All 69 people on board survived. They call it the Gimli glider. Fact number 4. Planes fly higher to save fuel. At 35,000 feet, the air is much thinner than at sea level. Thinner air means less drag. Less drag means the engines do not have to work as hard to maintain speed. The fuel savings from flying high are enormous. The trade-off is that the engines also get less air to work with. But jet engines are designed to compensate for this. The sweet spot, where the fuel efficiency of high altitude outweighs the engine performance penalty, is usually around 35,000 to 40,000 feet. Fact number 5. The autopilot lands the plane better than the pilot in certain conditions. Modern auto-land systems, the technology that allows a plane to land itself in zero visibility fog, are so precise that they can touch down within a meter of the center line of the runway consistently. In fact, in Category 3 instrument landing conditions, when visibility is essentially zero, only the autopilot is certified to land the aircraft. Human pilots actually are not allowed to hand fly the approach in those conditions because they cannot match the precision of the computer. So let us bring it all together. How does a plane stay in the air? It starts with the wing. That carefully curved airfoil shape creates a pressure difference. Faster air over the curved top, slower air under the flat bottom. Lower pressure above, higher pressure below. The wing gets pushed upward. That is Bernoulli. The angle of attack adds to this. The wing deflects air downward, and by Newton's third law, the air pushes the wing upward in return. That is Newton. The engines create thrust, pushing the aircraft forward fast enough for the wings to generate lift in the first place. Without speed, there is no lift. Flaps and slats allow the wing to change shape, generating enough lift to fly safely at the low speeds required for takeoff and landing. And the stall is the fundamental limit of every wing. The point where the angle of attack exceeds what the airflow can handle, and lift collapses. 15,000 kilograms of metal and fuel and people, held up by an invisible pressure difference of less than 2%, spread across 525 square meters of precisely engineered aluminum. The next time you sit by the window on a flight and look out at that wing, you will know exactly what it is doing. And maybe, just maybe, it will feel a little less like magic and a little more like the most incredible engineering achievement in human history. Because that is exactly what it is. If you enjoyed this video, subscribe. Because next week we are going inside a car engine. We are going to look at exactly what happens in those milliseconds when a spark plug fires, a piston moves, and 200 horsepower is born from controlled explosions. See you then.